Hello, I'd like to talk about technology that renders 3D objects onto 2D widgets. The objects don't participate in scene's physics or graphics pipeline, they don't cast shadows or reflect light. In early stage of Tsukurei's development, I wanted to draw an overlay that would visualize the forces acting on the racing car. Then I decided to go further, visualize wheel rotation, contact forces, suspension movement, air forces, and center of mass. They are drawn over the entire scene, including the car. They must be anti-aliased, not affected by motion blur or depth of field, and their resolution should not change when using upscaling a low resolution. The initial plan was to create several new instant static mesh components, each of them having an individual primitive like cones, spheres, squares, or cubes. Applying position, scale, rotation, color, each frame for each of these primitives. This object should be visible through the car, so the material should not take part in the scene depth test. In this case, we have a depth steps problem. You can see it. To avoid it, we should change render order depending on the distance to the camera. Another option was using a custom depth. In this case, depth problem is solved, but it can degrade performance. Both of these options have the same resolution as the game has, so at lower resolution, the overlay will also have a lower resolution. I also wanted more important components to be visible through the less important with some transparent halo around, so I needed more pixel control. But all the points I mentioned earlier were just an excuse. I actually wanted to use shaders for this, as I'm a shader. So to make all this stuff on the screen quad is a matter of the shader man's honor. The shader man's honor. We need to visualize 3D primitives on 2D plane without polygons. There are two basic options: ray primitive intersection and distance functions used in ray marshalling technique. There are two awesome resources with shader math created by Inigo Quilez: shadertoy.com and equilezless.org. Look on the screen. With SDF, we can create quite complex shapes with the cost of multiple iterations. But the shapes I wanted to implement are simple. That's why I chose intersection. But before the shader things, we should do Unreal things. Unreal things. Create a blank C++ project. Create a new map. I removed volumetric clouds and disabled lumen for better performance. Create blueprint based on default pawn. Not a regular pawn, it doesn't move with WASD. Now let's create an overlay widget. Tools, new C++ class, switch from common classes to all classes, type user widget, select user widget, name it overlay widget. Here is generated code. Create a blueprint based on overlay widget class. Name it bp_overlay widget. Let's add the next code in overlay widget.h. We added image and added binding in blueprint's requirement. Hot reload. In BP overlay widget, we get an error required widget binding. You should add image, name it mImageOverlay here, then it will be successfully binded. Place BP default pawn on your map. In Details panel, process to player 0. Press play or Ctrl P, and now we can see a full screen white rectangle. That's our overlay for now. Let's create an overlay material. Right mouse button in Content Browser, select Material, name it m_overlay, set material domain to User Interface, and blend mode to Translucent. Attach Screen Texture Coordinate node to Material Final Color output. Apply this material for image in BP Overlay widget. Now you can see the stretched UV on the screen. For SDF and intersection functions, there must be ray origin and per pixel ray direction, as we must cast rays. Let's overview the polygon rendering matrix multiplication pipeline. In polygon rendering, we must project world space vertex to screen space coordinate. In order to do this, we use transformation matrix that converts 3D model to projection space. Model view projection matrix is a multiplication of model, view, and projection matrices. Model matrix converts local space coordinate to world. View matrix converts world to view. It is inverse matrix of camera. Projection matrix converts view coordinate to screen space. But this is not our way. To cast rays to the primitive, we must go the opposite way. Convert normalized pixel coordinate to model space ray origin and direction. Project view model matrix is inverse of model view projection matrix. Project view model matrix equals multiplication of matrices projection inverse, view inverse, and model inverse. Pay attention that matrices are inversed and their multiplication order is inverse as well. We are going to use C++ to perform matrix multiplication. C++ things. The function is available to copy and paste from the article, but it is slightly modified here. So what does this function do? It gets owning player of the widget, set possess 0 in the editor. It gets dynamic material. If some of these is invalid, the image becomes invisible and we exit the function. Here, when everything is fine, we can update matrices and push it to the material of the M image overlay. As far as there are no set matrix parameter values in Unreal Engine, we use set vector parameter value. This function gets 4 float variable like f-linear color and transfers it into the shader. And we make widget visible if everything is fine. Hot reload. Go back to Unreal Engine. We will update this function every tick, so let's attach update overlay to the tick event. The next important thing is to use the matrix in shader and generate correct rays. Shader things. We will use this function in shader to convert pixel UV coordinate to ray origin and direction. But as Unreal doesn't receive float 4x4 parameter, we will slightly modify it and place this function in a custom node. First, we should declare the variables in the material parameters. Create 4 float constants, convert to material parameters, append RGB plus alpha, connect corresponding nodes. Oh, and add additional outputs to custom node, ray origin and ray direction. Paste the next code in custom node. Connect ray direction with final color. Now we see the ray direction debug view. It looks like we are inside a huge weird colored sphere. And finally, it is time to place some shape on a scene that will be raycasted. We will use this sphere for shape, kinda round cube. In Sucarays, the car overlay wheel shape is this. As you can see in the function parameters, ray origin and ray direction already exist. There is a radius variable as well. In order to make the radius 1 meter, we will set the variable to 100, as Unreal uses centimetric unit system. Let's copy this code. It is GLSL code, and we will make HLSL code. Remove function declaration and brackets. Declare radius variable, set it to 100. The result returns a distance from ray origin. Distance must be positive, otherwise there are no intersections. Place this code to the new custom node in Material Editor. Declare ray origin and ray direction inputs. Connect function output with the opacity. And now we can see this shape on a scene. The disadvantage of this specific shape is that the big ray origin offset causes this quantum superposition artifact. We will fix it next time. Note that this widget is full screen, which may be very inefficient to render. Next time we'll try positioning the widget only where it is needed. Also, we'll decorate this shape. That's all for today. Feel free to try it out. Please like, subscribe, and if you want to support Atsukure's development, you can buy it on Steam. Have a good day. See you next time. Bye.